Right? Vectors form a basis if the vectors span some subspace or vector space V, um, and the vectors themselves have to be linearly independent. Right? So when you're looking at, and this is what we were talking about with the column space before, so you have your entire column space, which is the listing of all the columns that make up a matrix. If you row reduce it to identify pivots, then what you do is what, I mean, it's not really called this, but I refer to it as the relevant columns because those are the ones that form the basis of the column space. Right? Those are the ones that are actually necessary to be there in order to define whatever the vector space it is that you're dealing with. Right? So the other ones are dependent on whatever the columns are that have the pivots in them. They might be necessary based on whatever context you're dealing with, whatever equation you're looking at might be useful, but in order to just simply define the vector space, the only ones that are absolutely necessary are those pivot columns, right? So those are the ones that show linearly independent relationships. So what do? We define a matrix, put it in reduced row echelon form, again, and then identify the ones that have pivot columns, right? And those would identify the basis of whatever the vector space is, right? So a couple of solved out examples, again, because they're very basic. This one should look pretty familiar. I actually took this and I changed it up a little bit and put it on your first test. It was talking about whether or not there was a linear combination or span, but that was kind of like a precursor. We want to know, is E1, 2, and 3 a basis in R3? And so, conditions, does it span? Well, yeah, it's an identity matrix when you put it all together, so of course it spans. And are they linearly independent? Yeah, all three of them, because they each have a pivot, right? So there isn't really much to address here, but this kind of, sort of, at least by definition, justifies why we use an identity matrix to form the basis of a real number system, right? So our I, J, K in R3, but just the I and J in R2, right? So 1, 0, 0, 1, where do those numbers come from? Well, they come from the idea that they span the entire system and they're also linearly independent, right? The two main components of something being a basis of a particular number system, all right? We have a linear dependent relationship here, right? So if you run this through your calculator, row reduce it, you see that you have a dependent variable, right? So because you don't have linear independence throughout, because the question is saying, are V1, 2, and 3 a basis of R2? All right, so the answer is no, because you have a linearly dependent relationship. But if I were just looking at V1 and V2, those do span the real number system, and they also are linearly independent. Right? So it's just that V3 is throwing it off. Now, if it just says, out of these vectors, can you form a basis of R2? You say, yeah, with V1 and V2, then call it a day, right? But because they threw in V3, it's not a basis, all right? And this is one of the typos. This should say linearly dependent. It's a legacy typo. I announce that correction every semester. Somehow, some way, even with typo bonus, I forget to change it. So look for it, right? So again, same deal. Row reduce, you'll see that you'll have a dependent variable among these three vectors. All right, so let's see, give it a look. All right, so again, we want to see if it's going to form a basis in R3. So we're looking for linear independence. Linear independence happens when you solve the homogeneous equation and you only get the trivial solution. So let's solve the homogeneous. Really, it's just 3 by 3 that we need. Go back. I tried the no looker. Only trivial solution, therefore linearly independent. V1, V2, V3 form a basis. Basis. For R3. All right. And again, that means that you can write any vector in R3 as a linear combination of these 3 vectors. And really, I mean, it's still coming back to the concept of spin. It's just we're looking at it in a different way. It's basically saying, is one of the vectors, one or more of the, well, I guess one of the vectors, within the span of the other 2 vectors? Because if that's the case, then it's living in the same plane that's generated by these 2 vectors. Let's say if you have V3 living in the plane generated by V1 and V2, then that would mean that the subspace is entirely based in that plane, which would in turn mean that these 3 vectors can't be a basis of all of R3, only a single plane within R3. Right? Because it's only living in that single plane. It's not shooting off in other directions from that plane. It's just living in that single plane. Right? So by looking for the trivial solution, we're guaranteeing that each vector plays a role in a particular dimension. This one handles the I dimension, this one the J, and this one the K dimension. Right? In a different way than you're used to, but it still gets the job done. All right? And as long as it accounts for each of the different dimensions, then you know that you have a basis. The whole point behind this example was for you to say that if you have a basis, then you have a vector that you can write in terms of your bases. All right, so I know that E1 is 1, 0 and E2 is 0, 1, for example. But in a minute, we're going to redefine and say that E1 is like 1, 7 and E2 is 3, 9, and those form a basis of a new system. And what will my coordinates be? Right? But if I write this, it's basically IJ notation. I mean, it is IJ notation. I'm just using E1 and E2 instead. I could rewrite this vector in terms of my 2 bases. And that is another way to think about bases, because you could always write your vector in terms of your bases. All right? But you'd have to be using all of them. Right? Otherwise, the vectors are not your standard bases. So same idea, but in 3 dimensions. And that just kind of brings it all together.